Have you ever wondered how self-driving cars work, or how Netflix recommends movies you might like? It's all thanks to artificial intelligence, or AI. AI is the ability of machines to perform tasks that typically require human intelligence, such as learning, problem-solving, and decision-making. AI is revolutionizing the way we live, work, and interact with the world around us. From healthcare to finance, transportation to entertainment, AI is transforming industries and creating new possibilities. But how do machines actually learn and think? At the heart of AI is machine learning, a powerful set of techniques that enables computers to learn from data without explicit programming. Instead of being programmed with specific rules, machine learning algorithms learn patterns and relationships from data, allowing them to make predictions and decisions on new, unseen data. In the next section, we'll delve deeper into machine learning and explore the different ways machines can learn. Imagine teaching a child to recognize a cat. You might show them pictures of cats, pointing out their distinctive features: pointy ears, whiskers, and a furry tail. Over time, the child learns to identify a cat, even if they've never seen that particular cat before. Machine learning works in a similar way. We train a computer algorithm on a large data set, providing it with examples and their corresponding labels. For instance, in our cat recognition example, the dataset would consist of images labeled as cat or not cat. The algorithm learns from this data, identifying patterns and relationships that distinguish cats from other objects. Once trained, the algorithm can then analyze new, unseen images and predict whether they contain a cat. This ability to learn from data is what makes machine learning so powerful. It allows computers to adapt to new situations, make predictions, and improve their performance over time, without being explicitly programmed for every possible scenario. Supervised learning is a type of machine learning where the algorithm learns from labeled data. This is akin to a student learning from a teacher who provides the correct answers during the learning process. In supervised learning, the data we use to train the algorithm is already labeled with the correct output. This means that for every input in the dataset, we provide the algorithm with the correct output, much like a teacher marking a student's homework. The algorithm's goal is to learn a general rule that maps inputs to outputs. By doing so, it can make accurate predictions on new unseen data. This process involves the algorithm identifying patterns and relationships within the labeled data. For instance, if we are training a model to recognize handwritten digits, we provide it with images of digits along with their corresponding labels. The algorithm then learns to associate certain patterns in the images with specific digits. One common example of supervised learning is spam filtering. When you receive an email, the spam filter analyzes its content and other features, such as the sender's address and the presence of certain keywords. Based on its training data, which consists of emails labeled as spam or not spam, the algorithm determines the likelihood of the email being spam and filters it accordingly. This helps in keeping your inbox clean and free from unwanted messages. The spam filter continuously improves as it processes more emails, learning from new examples and refining its predictions. This adaptability is a key strength of supervised learning algorithms. Another example is image recognition, where the algorithm is trained on a dataset of images labeled with their corresponding objects, such as cats, dogs, cars, etc. By learning from this labeled data, the algorithm can then identify objects in new images. This technology is widely used in various fields, from social media platforms that tag people in photos to autonomous vehicles that need to recognize pedestrians and other objects on the road. Supervised learning is widely used in various applications, including medical diagnosis, fraud detection, and credit risk assessment. In medical diagnosis, algorithms can help identify diseases from medical images or patient data, providing valuable support to healthcare professionals. In fraud detection, supervised learning models analyze transaction data to identify patterns indicative of fraudulent activity. Similarly, in credit risk assessment, these models evaluate the likelihood of a borrower defaulting on a loan based on historical data. Supervised learning is a powerful tool for tasks where we have labeled data and want to predict outcomes or classify data into predefined categories. Its ability to learn from examples and improve over time makes it an essential component of modern AI systems. as we continue to generate more data and improve our algorithms. The potential applications of supervised learning will only expand, driving innovation and efficiency across various industries. The future of supervised learning holds immense promise, and its impact on our daily lives will continue to grow as we harness its capabilities to solve increasingly complex problems. Section 4. Unsupervised learning, discovering hidden patterns. Unlike supervised learning, unsupervised learning deals with unlabeled data. This means that the data fed into the algorithm does not come with predefined labels or categories. The algorithm doesn't have access to the correct answers during training, making the process more exploratory and open-ended. Instead, its goal is to discover hidden patterns, structures, or relationships within the data itself. This can be incredibly powerful for uncovering insights that are not immediately obvious. One common application of unsupervised learning is customer segmentation. Businesses often have vast amounts of customer data but lack the means to categorize it effectively. By analyzing customer data such as purchase history, browsing behavior, and demographics, unsupervised learning algorithms can identify groups of customers with similar characteristics. These groups, or segments, can then be targeted more effectively with tailored marketing strategies. This information is valuable for businesses as it allows them to tailor their marketing campaigns, product recommendations, and customer service strategies to specific customer segments. This leads to more personalized customer experiences and can significantly boost customer satisfaction and loyalty. Another example is anomaly detection, where the algorithm learns the normal patterns within a data set and then identifies data points that deviate significantly from these patterns. This is particularly useful in fields like finance, cybersecurity, and healthcare. In finance, for instance, anomaly detection algorithms can flag unusual transactions that may indicate fraudulent activity. Similarly, in cybersecurity, these algorithms can detect unusual patterns of behavior that may signify a security breach. In healthcare, anomaly detection can be used to identify unusual medical scans that may indicate a rare condition or disease. This can lead to earlier diagnosis and treatment, potentially saving lives. Unsupervised learning is a powerful tool for exploratory data analysis, allowing us to uncover hidden insights and make sense of large, complex data sets. It's particularly useful when we don't have labeled data, or when we're trying to understand the underlying structure of the data. For example, in scientific research, unsupervised learning can help identify new patterns or correlations in experimental data that were not previously known. This can lead to new discoveries and advancements in various fields of study. Overall, unsupervised learning opens up a world of possibilities for data analysis, enabling us to explore and understand data in ways that were not possible before. Section 5. Reinforcement learning. Learning from experience. Imagine training a dog. You start with simple commands like sit or stay. You reward it with treats and praise when it performs a desired behavior, such as sitting on command or staying still when asked. Conversely, you might use negative reinforcement, like a stern voice or withholding treats, to discourage unwanted behaviors, such as jumping on guests or chewing on furniture. Over time, the dog learns to repeat actions that lead to rewards and avoid actions that result in punishment. This process of learning from consequences is fundamental to how reinforcement learning operates. Reinforcement learning works in a similar way. The algorithm interacts with an environment and learns through trial and error, much like the dog learning from its experiences. The algorithm receives feedback in the form of rewards for taking actions that lead to desired outcomes and penalties for actions that lead to undesirable outcomes. For instance, a robotic arm might receive a reward for successfully picking up an object and placing it in the correct location. Conversely, it might receive a penalty if it drops the object or places it incorrectly. This feedback loop helps the algorithm refine its actions over time. One prominent example of reinforcement learning in action is game playing. Algorithms have been developed to play games at a superhuman level. Reinforcement learning algorithms have achieved superhuman performance in games like chess, where strategic planning and foresight are crucial, Go, which requires deep strategic thinking and adaptability, and Atari video games, which test reflexes and quick decision-making. By playing millions of games against themselves, these algorithms learn optimal strategies and decision-making policies that can outperform human players. Through this extensive practice, they develop a deep understanding of the game mechanics and can adapt to various scenarios. Reinforcement learning is also used in robotics, where robots can learn to navigate complex environments, grasp objects with precision, and perform tasks autonomously without explicit programming for each specific action. This allows for greater flexibility and adaptability in robotic systems. By interacting with their surroundings and receiving feedback in the form of rewards and penalties, robots can learn to adapt to new situations and improve their performance over time. This continuous learning process enables robots to handle a wide range of tasks, from simple object manipulation to complex problem-solving in dynamic environments. As they interact more with their environment, they become better at predicting outcomes and making decisions that lead to successful task completion, showcasing the power of reinforcement learning in real-world applications.